Good morning, Professor. My name is Samjinti. Today, I would like to present a topic of my research work: structural behavior of post-tension precast concrete beams with corroded strands. The contents of my presentation today. An accident of YNYSY GWS bridge was due to the tendon corrosion. The bridge was regularly inspected, but there had been no evidence of deterioration before failure. Another one is Trojan Bridge was also collapsed due to the suspension cable's corrosions. The inspection was done within every 2 minutes, which means 2 minutes earlier there had been no evidence of deterioration or nothing extraordinary, but 2 minutes later the bridge was already collapsed. This showed that the tendon corrosion is a very critical issue and dangerous that need to be improved and solved. And an access to inspect the corrosion of strand in the PSC beam is required to evaluate the condition of the corroded strands. Unfortunately, the embedded strand in the PSC beam is severely limits access for inspection. And to have this study begin and have a clear direction, some previous research works are reviewed and highlighted here. These research works have slightly different from this study in terms of objectives, methodologies, and techniques they use and how they conduct the experimental tests. Most of this research work were more focused on the initial stiffness and cracking, while in this study we focus on post-tension precast concrete bridge with artificial corroded strands. We also adapt ICM and electrochemical methods as well as strain gauge. And our main focus is on global and local behavior at the ultimate limit states when the wire fractures. The main question of this research work is how to investigate and evaluate the ultimate limit state behavior of the PSC beam with corroded strands. To answer and accomplish this question, a few things need to be done. We produce PSC beam with different level of corrosion strengths, conducted corrosion induction test for each specimen, conducted fractal test, we conducted analytical study, and lastly we conducted the parametric study to even a broader understanding of the behavior of PSC beams. And this is the scope and the outline of this research work. There are three PSC beam specimens were manufactured and for this study. CCB, which having the corroded strand located at midspan. Another two specimens are CB1 and 2, which having the corroded strand located at section C, 300 millimeter from supports. This is the strain gauge plan of this study. The name convention ACO125, BCO125, and CCO125 is indicate the concrete strain gauge in each section, and the name convention A or E, B or E, COE from 1 to 4 indicates the rebar strain gauge in each section A, B, and C as well. And this name convention will be used throughout these research works. There are three important steps during the experimental tests. Number one is precessing force is applied to every specimen. After that, every specimen was induced corrosion, and then conducted flexural tests for every specimen. After the flexural test, the test parameters in terms of loads, displacement, and strain that we focus on in this study can be drawn at each section, as you can see here. Since strain gauge couldn't attach to the strands, therefore there is no strain or strand from the test results. But to investigate the behavior of post-PSC beam with corroded strands, we must consider the strain or strand and its effects. Therefore, in this study, we need to estimate the strain or strand using this following equation, including the strain incompatibility method. After the conducted flexural test, each specimen was broken down and cut only the corrosion strength section to measure for pit depth. To inspect the corrosion strands, only the deepest pit depth along the corrosion strands is measured using this pit depth gauge. There are three types of pit depth configurations, and each type have different empirical equation to calculate the loss of a sectional area. And from that, we can calculate this section loss of its specimens. As a result, CCB specimen with a 36.64% experience three-wire fractures, and ECB1 with a 39.8% experience five-wire fractures, and ECB2 with 0.4% of section loss experience no wire fracture at all. And it shows that when the section loss of the corroded strand is increased, the maximum load is decreased, and when the maximum load is decreased, the flexural maximum displacement also decrease as well. And also we see that the most corroded wire influence the global behavior of the PSC beam with corroded strands. All three specimens are compared in each section, and the local behavior was observed. From this graph, it shows that in section A, CCB tend to have larger strain development. In section B, CCB also tend to have larger strain development as well. And in section C, ECB1 tend to have larger strain development. So as a result, it showed that when the amount of section loss is increased and the strain measurement located near corroded strand, it, it's resulting in larger strain development. And when the amount of section loss and the strain measurement location far from the corroded strands, resulting in smaller strain development. Summary for the experimental study, we see that the most corroded wire govern the global behavior of the PSC beams. When the section loss is increased due to corrosion, the maximum load capacity of that strain is increased. The location and level of corrosion strain in the midspan show a significant behavior change in terms of load and strain of the corroded strand in the PSC beam, and the level of corrosion influence local behavior of corroded strand in the PSC beams depend on the location of corrosions. In the analytical study, the equivalent material model for corroded strands proposed by previous researcher is adopted, and the equivalent material model of a specimen can be estimated using these empirical equations. Concrete and rebar material are based on Eurocode 2, and CDP concrete damage plasticity model is used for concrete properties, also based on Eurocode 2, and the main parameter for CDP model is based on the standard value as shown in these figures. The equivalent material model derived from these empirical equations are used for abacus input data, and the displacement control method is used in this study, and the mass size about 20 millimeter is used, and the predefined stress of 870 megapascal is used in this study. In the equivalent material model, we define the ultimate strain of CCB of 9,000 microstrain, and the analytical record as shown in this picture that the estimate strain when the wire fracture was about 8,945 microstrain. At a certain point, the load was about 250 kilonewton. As a result, from this graph, it showed that for non-corroded strain, a 1.42% difference in terms of load and 2.85% in terms of displacement. As for corroded strands, the 14.95, about 14% different in terms of load, and 38.19% in terms of displacement. This gap difference is the reason that the corroded strand have a larger error is because the limitation of the equivalent metric model that we adopted. So as a result, it showed that both analytical model of non-corroded strand and corroded strand show a good, reasonable, and a good agreement with the analytical model. For comparison of each specimen, I choose the strand strain in section B. Um, as a result, it showed that about 12% in different internal strain for ECB and 5.9% in terms of ECB1. For ECB2, there is no data of ultimate load and strain at fracture stage due to compressive concrete crush earlier, and the amount of section load was too small. To summary for the analytical study, the concrete and rebar material model used in this study is followed by Euraco 2. The section loss of the more corroded wire was used for building a material model of the corroded strands, and concrete damage plasticity is used for concrete property, and the Abacus commercial software is used for finite element modeling. To conduct the parametric study, a verified analytical model is used, and the location of corrosion is chosen as shown in these pictures, and level of corrosion from 0%, 3%, 10%, and 30% is selected for the case study. Both case of 0% and 3%, as we can see here, show no different at every locations. As a result, the location of corrosion at a distance of smaller or equal or smaller than 650 meter show no effect on corroded strand local behavior of the PEC beam uh, when the section loss is smaller than 5%. The corrosion location at a distance of equal or smaller than 650 mm from support show little to no effect on the local behavior of PSC beam corroded strain when the corrosion level, even though the corrosion level is higher than 5%. However, the effect of corrosion level started to show significant change when the corrosion location located at a distance of equal or larger than 950 mm from supports, with the corrosion level of higher than 5%. The key findings from this research work are as follow. When the section loss is increased due to corrosion, the ultimate load capacity of that strand is increased. The section loss of the more corroded wire govern the behavior change of the PSC beam member. The level of corrosion significant influence the behavior change of the PSC beam member depends on location of corrosions. The higher amount of corrosion strength causes wire fracture earlier before compressed concrete crushing. The effects of corrosion level started to show significantly change when the corrosion is equal or higher than 950 mm from the port, with the corrosion level is higher than 5%. So, as a conclusion, when the amount of corrosion increases, the ultimate strain developed is increased. Moreover, the significant behavior change in terms of ultimate load and strain when the corrosion level is higher than 5% and corroded strain located not less than 950 mm from supports. Thank you very much for listening.